Thanks for the kind invitation and giving me the opportunity to make this presentation. I am going to tell you about IceCube and about discovery we made of cosmic neutrinos. But as this audience may not be very familiar with the topic, I'll try to give some introduction. In fact, I should have heard the word kilometer cube detector in 1969, except I was a student doing particle physics. But that was the year that Berezinski and Zatsepin made the following simple calculation. Let me first describe the plot and then the calculation. This is a plot Turner made in 1990, and it tells you what the diffuse flux of photons is in the universe. And you see this flux stops around hundreds of GeV. And then the universe, the sky, is dominated by cosmic rays, not by photons. And in fact, this is a very interesting region. I come back to this at the end of my talk. So the idea was to do neutrino astronomy at hundreds of GeV on. And what Berezinski and Zatsepin calculated was the following. They knew that the highest energy cosmic rays, they have energies of 10 million times the energy of the LHC beam. They knew they had to be extragalactic. They have a gyro radius that cannot be contained in our galaxy. So that means that since the beginning of time, these cosmic rays live in the same place as microwave photons. So you can calculate the collisions, how often the cosmic ray beam meets the 410 photons per cubic centimeter, and how many pi pluses are produced since the beginning of time. These pi pluses decay in neutrinos. You can do this on the back of an envelope, and you get the answer that if you build a kilometer cube neutrino detector, you will see one event per year. In fact, the answer for IceCube is 0.5. And we should have seen several events by now, and we have not. It's become interesting, but that's a different talk. However, this one event has an energy of 1 million TeV, so it's very easy to detect. So you get excited despite a small number. But, you know, we thought we had to find better arguments to ask for money to build this detector. And so over the last couple of decades, a logic was developed. You heard from the previous talk that it's difficult to go and look for the cosmic accelerators. Even the galactic accelerators we don't understand. As you heard clearly, you know, you got this beautiful data and they just raise more and more questions about what the sources are. And of course the situation is not better for extragalactic accelerators. So one thing we do understand is the sun. And when there is a solar flare, a day later, 10 GeV protons arrive at Earth. And so you have these relativistic particle flows, and somehow nature knows through shocks or reconnections how to accelerate particles. The 10 GeV is not a mystery. In order for the picture that I showed to be an accelerator, the gyro radius of the particle has to be contained in the accelerator. If you don't contain it, there's no time to accelerate. That means that E over B has to be smaller than the size of the solar flare. So if you put in the magnetic field and the size of the accelerator, you get from this that the energy is at most 10 GeV, and that's what we see. Now, the problem with cosmic rays is not only that the energies are high, this takes a little bit more work but all the luminosity are extremely high. And so if you try to extend this picture, where can you find bigger B fields and larger B fields? Well, the general idea is that you look for the collapse of a star. And you tap its gravitational energy to accelerate particles. So this is a star that collapsed a few hundred years ago. You see these flows and we know particles are accelerated there. We see it, for instance, in TV gamma ray experiments or in X-ray experiments. While this can explain galactic cosmic rays, extragalactic cosmic rays can really only be explained by something more powerful, and that's the star collapsing to a black hole. The same thing happens, except it happens in seconds. That's a gamma ray burst. And so these are logical candidates for cosmic ray accelerators. The problem is that we have looked for neutrino emission from gamma ray burst for many, many years now. We have looked at almost 1,000 bursts. The astronomers tell us when they happen and where they happen. We have never seen a neutrino. In fact, the limit on the flux from gamma ray burst is now at a few % level of the flux we discovered that I'm going to talk about later. Fortunately, there are other ideas, not too many actually. This is about it. This is an active galaxy, and now you use the same kind of ideas using the supermassive black hole, and on the inflows of the jets, you get opportunity for accelerating. So what I want to point out is that there is a generic picture of what the answer can be. There's somehow a black hole and neutron star involved. But important for us, these objects are surrounded by dust and radiation. That means you not only have an accelerator, you have a target for producing neutrinos. This is what at CERN you call a beam dump. And so you can model this generic picture. And so in the P-gamma interactions, for instance, the target in the beam dump could be the light surrounding the star. You produce pi pluses, and theorists have been doing these calculations for decades now. And one important thing, if you produce a pi plus, you also produce a pi zero. So for every high energy neutrino, there has to be a high energy gamma ray. Remember that, I'll come back to that later. If you collide on protons, it's the same, there is a factor difference. So this picture summarizes the result of that exercise. Okay, so this is the neutrino flux predicted times the energy square, which is the typical prediction of shock accelerated beam. And so the predictions form a flat line, horizontal line. And you see here the shaded region is the prediction for neutrinos from supernova remnants. There you see the prediction from gamma ray burst. And that's actually the flux I mentioned first, the one event per year produced by cosmic ray interacting with microwave background. Notice they all kind of line up. And important here is that if you translate this, you get in this decade, you get 10 to 100 events per year if you build a kilometer cube detector. So it's better than one. But of course, these calculations have errors that I wouldn't even want to try to estimate. What is this? This is the atmospheric neutrino flux. Of course, if you look up at the sky, you see neutrinos. In fact, as I stand here, IceCube detects one every 6 minutes. And they are produced by cosmic rays hitting the atmosphere. So cosmic rays enter the atmosphere, make pions, same mechanism, make neutrinos. And even a mile deep under the Earth, you see, if you have big enough detector, you not only see neutrinos, you see also the muons that survive. So the idea of building a kilometer cube detector is even older. It goes back to 1960. And Markov's idea, I have pictures on the next slide. It's very simple. You build a Cherenkov detector. His idea was you go deep in the ocean, imagine a kilometer cube of clear, dark water. You fill it with photomultiplier tubes, and so you look for particles coming through the Earth. If you see a muon coming through your detector, only it cannot have penetrated the Earth, so it must have been deposited inside or near your detector by a neutrino. And this is a very efficient mechanism because at the energies I'm working, muons have a range of kilometers to tens of kilometers. And the other thing is, if you map the Cherenkov cone of the muon, you know its direction, and at these energies it's aligned with the neutrino. So you not only have neutrinos, you have a telescope. So you make dots at the other side of the Earth, so from the South Pole, you detect neutrinos above Rome, and every neutrino is a pixel in a map, and that map is what you want to get. If you can get rid of the 6 atmospheric per minute. So our idea was slightly different. We did exactly the same thing, but put the photomultipliers a mile deep in the ice rather than in water. So at this place here, you are 800 miles from the 800 meters from the geographic South Pole. If you go a mile deep, we took a kilometer cube of ice and filled it with 5,160 photomultipliers. There's also an air shower array covering the experiment. How we do this is more fascinating than my talk, but I won't go into that. For the theorists, this is a 10-inch photomultiplier, and there are 5,160 of this, and they detect the Cherenkov light. So it's extremely simple. If you could go into the experiment, you would see these kilometer-long strings with every 17 meters of light sensor. And if you look 125 meters away, you would see another string of 60 of them until you fill a kilometer cube. It's important in this experiment that the signal that comes out of the photomultiplier is actually captured at the photomultiplier and digitized. And then it's sent over the same signal, the same cable that brings down the high voltage. The signal is sent back. And so what you receive from these photomultipliers are digitized signals like this that count the number of photons as a function of nanoseconds with a precision of 2 nanoseconds across the detector. So if you didn't get it, this is a cosmic ray muon entering. When it enters the detector, there is a Cherenkov light, and you see the photomultiplier slide up. The color tells you the direction, and the size of the dots tells you how many photoelectrons were detected. That's the propaganda. This is what a muon really looks like. This is a 93 TeV muon. And you see, well, it's hard to see the Cherenkov cone. You can actually see it. But what you may mostly see is these explosions of light. And what that is, a 93 V muon, forget minimum ionization, a 93 TeV muon just emits gamma rays, produces electron-positron pairs, occasionally produces pions. And these showers of secondary particles create Cherenkov light. And so when you put together the signals sent to us by the photomultipliers, you see here the number of photons as a function of time. This is a 1.1 kilometer muon track. And so we actually made a big breakthrough when we actually started mapping in detail these structures and reconstructed the energy and the direction from this information. By the way, 100 TeV muon comes typically from a 5,000 TeV neutrino on average, and this has 100,000 photoelectrons in the signal. So what do you detect? You detect atmospheric muons most of the time. You detect atmospheric neutrinos from everywhere on Earth, and so that results in this. You see, this is IceCube taking data. There is no detector. All you do is there is a computer at the surface which you are looking at that collects all these signals from these 5,160 independently running experiments, and then it puts it together in tracks. Here you see a muon bundle coming through the detector. And so these tracks are reconstructed in real time. And this movie repeats, and it's 10 milliseconds long. So what that means is that, similar to the previous speaker, we actually collect something like 100 billion muons per year, 3,000 per second, 100,000 atmospheric neutrinos per year, 1 every 6 minutes. And remember, we are looking at 10 to 100 events. Fortunately, the answer was close to 100. So this is a 100 TeV neutrino. We detect one of those. It goes red to green to blue. So that comes through the Earth. You follow the rainbow. And this still has a possibility that it could be produced in the atmosphere. I come back to that on a later plot. In fact, we now think that this is more likely to be a cosmic neutrino. And we detected them at a range of like 1 a year when we were building the detector. After running the completed detector for 2 years, this is the neutrino. The muons have been removed. So this is the neutrino flux, the atmospheric neutrino flux. The threshold of IceCube is about 100 GeV. Most of our neutrinos are in the 1 TeV range, so you see the number of events rise. Then you see what's predicted, measured and predicted, is the atmospheric neutrino flux here. And you see when you come to 100 TeV, you see this deviation. The data doesn't track the atmospheric flux anymore. This is a 3.7 sigma effect. And in fact, what you see, which will be published in PRL, Physical Review Letters, next week, I think. And what you see, of course, is exactly what's on this plot. When this 5 is 10 to the 5 GeV, when you come to 100 TeV, you begin to see sources, exactly as predicted. And we are at the very high end of this prediction. In fact, here is an event. After we added a year of data, this went to 4.3 sigma. In a few weeks, we will have added another 2 years for those of you who like 5 sigma. It's there. This deposits 950 TeV just when the muon passes through the detector. And is a neutrino, is of course the parent, is several thousand TeV neutrino. Now, for those of you who follow this field, you realize this is actually not how we discovered cosmic neutrinos. We discovered them in a more clever way, which was not, it was supposed to be this one, it eventually worked. Oops. Yeah. So what we are actually doing was looking in our first 2 years of data for this event. And we didn't see it, but in the analysis where we were, it was a blind analysis looking for the event, we found serendipitously, we found this event, which, as you see, the light starts close to this string, goes up and down the string, then it arrives sometime later at the strings that are 125 meters away. Now it arrives at the next string. And you see there is no muon track. That's not a surprise. It's an electron or a tau neutrino. What's a surprise is the size. From the amount of light, if you have a bit of experience, you can immediately tell this is not a 100 TeV event, this is 1,000 TeV events. And so the fit confirms this. And so we found 2 such events. So what this means, so what you are looking at is an electron neutrino that interacts in the detector. It gives 80% of its energy to an electron. The electron makes an electromagnetic shower, and the shower particles emit Cherenkov light. This electron shower has about the size of 5 to 10 meters. It's smaller than this room, which in a kilometer cube detector is like turning on a light bulb, which is exactly what you saw. However, thanks to, by the way, this is a muon track that has exactly the same energy. So this is a muon neutrino of the same energy as the shower you saw. Now, you have to realize, in case you missed what a kilometer cube is, this is the event superimposed on the data center in Madison. This is the lake, if you have ever been there. So you imagine the size of the event in Rome is like 6 city blocks. That means with 2 nanosecond resolution, you track light over 6 city blocks. And that has an important consequence. So I'm now going to show you a simulation of the event. Notice it's spherical, it's a light bulb, but notice it's red here, yellow here. Now it turns yellow here, blue here. And so when you actually look at the timing of the photons and not the shape of the shower, you recognize the direction of the electron. This electron came this way. And so these photons arrive earlier than those photons. And so remember, each of these dots is a trace of light, of photons. And so you fit all these traces, you can reconstruct the direction. We are still working at this. Our limitation at the moment is computing time. These events have 100,000 photons in them. And so, but you know, Moore's law will solve that soon. Let me skip this. So we detected 2 of those events, and the probability that these are cosmic are at a 3 sigma level. And we didn't really publish, we published them but didn't claim anything. But you notice the importance that they were contained. You had a calorimeter that measured the whole energy. So everybody had the idea, it was actually in the proposal, the idea, to build a veto around IceCube. This veto is about 6 layers of photomultipliers on top and 1 on the sides and the bottom. And you look for events that start in the detector. You look for a neutrino that interacts, you trace back the direction, and you require no light in the veto. And we did a complicated analysis, but if you just plot the data, you see the signal. This is the data of 1 year versus the number of photons in the event versus the number of photons in the veto region. So in other words, in this plot, you go from low to high energy here, and this is the veto region. You want no photons in the veto region. And you see here, you see the signal stick out. And we have by now looked at 4 years of data, and every year looked exactly the same. And so this signal is now something like 7 sigma. We published this in 2013, and in fact in the next year of data we found a 2000 TeV event, and we have now doubled the data. And so I will show you what happened after doubling the data. This is a projection. Again, this is the plot, just number of events versus number of events versus the energy. And you see here again, this is the atmospheric background, this is the signal, and this is exactly the same flux as this flux. This is now 7 sigma. These are mostly, there are nu mu's in these events. They are mostly nu e, nu taus, because nu mu's are absorbed at these energies coming through the Earth. But the flux that I described before, looking through the Earth, is exactly compatible with this flux if you produce equal numbers of electrons, muons, and taus. Obvious question, where do they come from? And so you make a map. As I said, each neutrino is a pixel in the sky. And this is the 4-year map. There are 54 events in this map. We were caught by 1 background event, which we removed actually. And so this flux is totally uniform. There's no evidence for any clustering despite the artist's attempt at coloring this concentration of events. It has no significance. In fact, the best way of looking at this is these were the events after 2 years, and these are the events after 4 years. And in fact, any evidence for this has not grown. Any correlation to the galactic plane, this is in galactic coordinates, the galactic plane is there. If you think you see a correlation there, it has not grown in 2 years. So this is a uniform flux. We actually do measure the flavor composition, and to make a long story short, it's 1 to 1 to 1. So what we are seeing is a diffusive extragalactic flux. We cannot exclude a small galactic component, but it's certainly not dominant. And remember, I told you for every neutrino in this map, there is a gamma ray. No one has ever seen a PV gamma ray. They're very easy to see. You can detect them with air shower rays if you have a few muon counters underground, and it has been attempted. So this is not a mystery. So every neutrino has a gamma ray going with it. This gamma ray doesn't make it to the Earth. It cascades in the microwave background and in the infrared light in the universe. And so you can calculate, you just take for every neutrino a gamma ray, propagate them to the microwave background, and see where you end up. You end up with lower energy photons. And so here is the result, which I think is fascinating. There's no fitting here, no theory, no nothing. You just draw through the IceCube data, you draw e to the minus 2.15 power, with or without a cutoff, it doesn't matter. You cascade the equivalent photons, and we fit exactly, we don't fit. We predict, this power predicts exactly the Fermi flux. Extragalactic flux. So, one point of warning, however, this cannot be the whole story, because you see here there is an excess. In fact, this is a different analysis, and you see here this excess. There's something more going on that's significant. I don't know what that is, but I think the overall conclusion is interesting, because you would think that after building a big detector for 25 years, you're looking at something exotic. This suggests that we are looking at a whole sky, just like Fermi and like the TV gamma ray experiments. And so that means you can really do neutrino astronomy. You're not doing something esoteric. So you can now turn this around, and I'm not going to explain this slide, but I can take the photon sources that they see and convert it to neutrinos. And so I predict in 5 years of data, which we are now analyzing, we predict of the order of 10 events from the sources that Fermi sees. And as we are allegedly seeing the same sources, we'll discover sources soon. So of course, you can start betting, because this now means most likely that we are either seeing active galaxies, most likely blazars or starburst galaxies. And so we are going to confirm this by doing detailed catalog comparisons between Fermi sources and, in fact, between high-energy Fermi gamma rays and high-energy neutrinos. So I don't have time to discuss the future, but I just want to show a few slides. You want to do astronomy with neutrinos only. Multi-wavelength is beautiful, but you want to do neutrino astronomy. And it's a back-of-the-envelope calculation, which you can see in papers, that instead of hundreds, you need thousands of events to see 2, 3 neutrinos come from the same point in the sky. That's real astronomy. So how do you get 1,000 instead of 100 events in a few years? You build a 10 times bigger detector. And then, instead of a discovery instrument, you have a telescope. Is this easy? It's extremely easy, because by building IceCube, we discovered that the absorption length of light is more than 100 meters. In fact, it's over 200 meters in part of the detector. The clearest Kamioka water, Super K water, has an absorption length of 80 meters. So it means you can space these photomultipliers, to do the physics I explained, by 250 meters. And you can actually get all this, let me skip that, and get all the same results, same performance. In fact, we tested this by taking half of the strings out of IceCube. You almost lose nothing. And so somewhere between 250 and 300 meters, you can instrument 10 times the volume with the same number of photomultipliers. Same money, same techniques, it's boring. You just repeat it, but except putting the strings under 25 meters, you put them 250 meters apart, maybe slightly more. This is the propaganda picture. So I did not talk, I have to say this, I did not talk. We have by now like 500,000 atmospheric neutrinos. Of course, a large fraction of the collaboration is doing neutrino physics with this. So we did measurements of the oscillation parameters at high energy, which was a new test of the three-neutrino paradigm. I did not talk about supernova detection, about the search of dark matter. I wish I had another talk. We are looking for EV mass sterile neutrinos. Very interesting, given the result of 3 neutrinos we heard from the cosmologist. So before concluding, I want to show you this picture. This has nothing to do with IceCube. This is a string of light sensors that's sitting in Marseille, about to be deployed. And so I want to draw attention to the bottom of my final slide, that there is a similar effort going on both in Lake Baikal and in the Mediterranean to build a detector like this. And I think it's well justified at this point. You know, you don't argue among astronomers where you need more than 1 4-meter mirror. We need many of these detectors, and let's start with 2. And so these are my conclusions, but I mean the real goal of this experiment was actually to go and find something new, which I think we still will, because neutrinos are never boring. Thank you for your attention.
So thank you, Francis, for this beautiful lecture. Time for a couple of questions. I have one. I'm very much surprised. How ice could be cleaner than distilled water?
It's snow that fell on Antarctica typically 100,000 years ago. It's ultra pure. And so the purer is the same with water. The more you purify water, the larger the absorption length is. It's that simple. And so this is ultra pure snow. And in fact, you saw these peaks and bottoms and valleys. That are periods, you know, the winds go across Antarctica in a circle, as you know from the Anita experiment. And so when there are deserts in South America, a little bit of dust moves into that ice, and that gives you a worse absorption length. So we can track these structures and compare them with ice cores, and they perfectly match. But so it's just the purity. There's no mystery.
Okay, question. Where? There.
Yeah. Is it? Oh. Regarding the extragalactic potential sources, it seems that blazars, I mean, according to the calculations, are not favorable. On the other hand, low luminous agents like radio galaxies might be more suitable. Could you comment on this?
No, I mean, we'll find out by comparing maps. And we will get the answer. So I certainly don't want to speculate. But certainly the story we always heard that everything in the universe is an electromagnetic accelerator cannot be true. And it may not be true for blazars as well. We'll find out.
Another question there, and then we close.
Have you ever seen this type neutrino change its direction and energy? Have you ever seen any event? This type neutrino comes in, and then at a certain point, it changes direction and loss in energy?
No, remember, we only see it when it interacts, right?
Yeah, but I say if you have some other interacting, you don't see the signal like Cherenkov, but you see the neutrino beam bending and then maybe lost energy.
No, I mean, we assume
any
that
event?
we measure the direction of the Cherenkov flight and we reconstruct a neutrino from that.
That would be
And so-
a real discovery, yeah? Would be
Yeah.
a real discovery, seeing something like that. Okay, so I thank you again, Franz, for
Thank
this
you.
beautiful presentation.